So far in this lesson, we've seen how quick and efficient the power rule is for taking derivatives. We've also seen how if we can rewrite a function, we looked at negative exponents in the past video. If I can rewrite a function as x to a power, then the power rule is in play. So let's look at another example. We saw negative exponents last time. Let's look at another type of function where maybe it's not originally presented as x to a power, but there's a really quick and easy rewrite that can make it work. Let's look at f of x equals the square root of x, and I want to know what is f prime of x. Well, just like in the past, what I'm going to do, it's going to be very similar to what I did where I had 1 over x to some power and I was able to rewrite it as a negative exponent. If I can write this as x to a power, then I can take its derivative using the power rule. So the first thing I want to do is I want to take f of x equal to the square root of x and write it as x to a power. And remember, I can do that because really what this is it's the second root of x to the 1 power, and so I can rewrite that as x to the 1/2 power. So I want to rewrite, instead of with negative exponents, I want to rewrite it with a rational exponent. And then I want to apply the power rule. So if f of x is x to the 1/2 power, the power rule says that f prime of x, the power becomes the new coefficient, so 1/2 x. If I reduce 1/2 by 1, it becomes minus 1/2. So I apply the power rule. And then kind of like what we saw in the previous video with negative exponents, I need to do a little bit of cleanup after this process happens. So f prime of x is equal to, well, this negative exponent is going to send it down to the denominator. So this is 1 over 2 x to the 1/2, which I can then rewrite as 1 over 2 square roots of x. So my last result was to simplify f prime of x. And I can do that with any derivative. So there's the derivative of the square root of x. It's 1 over 2 square roots of x. I'm going to tell you now that we've kind of shown what that is equal to. It's going to be very helpful for you to know, and by know, I mean kind of memorize that. It'll be helpful to know that the derivative of the square root of x is always going to equal this value right here. It's going to be a lot of times in this class where we're taking the derivative of the square root of things. And just to already know without having to do this each time, that the derivative of the square root of x is 1 over 2 square roots of x. That's a very helpful thing just to know, hey, that's the derivative of the square root function, is it's always this form, 1 over 2 square roots of x, because it comes up a lot, like I said, that we'll take the derivative of the square roots of things. So kind of an interesting thing happened here. I've got the square root of x, which is not anything rational. Its derivative came out to be rational. Because it was to the 1/2 power when I reduced it by 1, it became a negative exponent, which sent it to the denominator. Now in a previous topic, in fact in the previous topic, 2.4. In topic 2.4, we mentioned, the whole point of that topic was we talked about functions that were continuous, but maybe because of a particular reason weren't differentiable. So we said that g of x, I said that the cube root parent function, the cube root of x, was not differentiable at x equals 0. And when we kind of sketched the graph of that cube root of x function, I told you that at x equals 0, it wasn't differentiable due to what I called, or what I told you was a vertical tangent line. And if you can't see a vertical tangent line, because sometimes they are kind of hard to visualize, you're really kind of taking my word for it that the derivative was undefined at 0 for this function because of that undefined slope of a vertical tangent line. But using the power rule, you can kind of analytically see what happens at x equals 0, the derivative of this function. So using the power rule, we can show that g prime of 0, or the derivative at 0, is undefined. So if I take g of x equal to the cube root of x, I can now use the power rule to rewrite the cube root of x as x to the 1/3 power. That means that g prime of x is equal to 1/3 x. If I reduce the power by 1, I get -2/3, which ends up equaling 1/3 x to the 2/3. And if I rewrite that as a root, you can see it's 1/3 cube root of x squared, kind of packing it nice and neat back together here. Well, what is g prime of 0? Well, g prime of 0, because of this nature that the derivative forced its x down to the denominator, if I plug 0 in here, I get the cube root of 0 squared, the cube root of 0, 3 times 0. You can see clearly that g prime of 0 is undefined because it would equal 1/0. So g prime of 0 is undefined because 0 is not in the domain of g prime of x. If I gave you this function, you would automatically tell me, hey, 0 is not in the domain. So that means that 0 is undefined for this function. G prime of 0 is undefined. That means the rate of change of g at 0 is also undefined, and that's what kind of generates that vertical tangent line that we graphically looked at back in topic 2.4.